actually still affiliated with Stanford. So I'll tell you a research story that sort of blends the work from these two institutions, and then think about, maybe how that links to what we're going to be doing here at Illinois, which I'm very excited about. And as was mentioned, the talk title is about this dream, which is building this quantum internet, so I'll tell you what that is, and how we can do that by harnessing photons, which is why I'm here, and also how we can harness electrons and their spin, sort of the magnetic moment of an electron. And so there will be a lot of sort of quantum science technology in this talk, but there's also going to be sort of a key photonics link, which hopefully will excite some of you, and we can sort of discuss what the challenges are there. And so, given that this isn't a quantum seminar, I'll go through this one slide for half a second, which is, when we think about engineering quantum technologies, right, we're harnessing the power of quantum physics, which gives us some unique strengths. So if we think about information in the world around us, it's encoded in the states of real world objects, that sort of are described by regular physics. So you can think about electrons flowing or not flowing through a transistor, encoding 1 or 0, or maybe magnetic domains in your hard drive pointing up or down that encode long-term memory. But quantum physics tells us that we can have more than just occupying one of these two states, that we can occupy this larger dimensional state space, which we describe with this so-called Bloch sphere. And if we take a quintessential quantum particle, which is just an electron, and we apply a magnetic field, its spin states, or its magnetic states, split into two by the Zeeman effect, giving us sort of two discrete energy levels that we can occupy that basically look at that electrons either aligned or anti-aligned with that field. But what this Bloch sphere really tells us, and what sort of quantum mechanics tells us, is that we can also create states that have these unique superpositions of being something like up and down at the same time, with this unique quantum phase that simply just describes where we are in this larger dimensional state space. And when I say the word coherence time, I really am just saying, if I create one of these superposition states, one of these unique quantum states, how long does this phase last before it sort of gets scrambled and interacts with the environment? And then of course, there's not just superposition, there's also this property of quantum entanglement, where the measurements and operations on one qubit can instantaneously affect another. And of course, this is famously what Einstein called spooky action at distance. And the reason that people are excited about this is because all of these features in quantum physics lets us design and build new devices that give us new ways of communicating, new ways of sensing, and new ways of computing. So quantum computers are these sort of buzzword topic that everyone wants. But what I'll be focusing on is not quantum computing, but something a little bit different. And it's this idea of a quantum internet. And so I'm really sort of always in awe of the regular internet, about how our cell phones talk to satellites in space to give us internet, and we have Zoom calls across the country. And all of that technology and all of that sort of societal and technological advance is underpinned by this huge infrastructure we take for granted, which is basically the distribution of the distribution of information at long distances with routers and amplifiers, things like modems to hook our computers up to those networks, and then of course the computers themselves that have the capability to do this. And so what I get so excited about sort of in my research is, how do we translate all of that sort of backbone infrastructure to the quantum world? How do we build quantum routers and amplifiers? How do we build quantum modems? And that's sort of what I'll be focusing on in the rest of the talk. And the reason that you would care to do this is, if you're able to realize this dream of a quantum network or a so-called quantum internet, you can do really cool applications like distributed quantum sensing, making modular, powerful quantum computers in the same way we have, computing clusters that are linked by the regular internet, making sort of, AWS cloud services and things like this. We can do that for quantum computing. And then we can also build things that sort of have secure communications, where our communication is fundamentally secured by the laws of physics, using the power of quantum physics. And so the dream that I'm hoping to sell you is taking this quintessential quantum two-level system, a single electron, and then using light to couple them together quantum mechanically. And maybe I don't have to convince you all, but light is sort of the only reasonable way that you could think about doing this, right? Light travels at the speed of light, sort of infinitely fast. It's wide bandwidth, and you can confine it into optical fiber and sort of distribute it all around, the city, the state, the country. But maybe what's less obvious is there's also this other feature of photons that we like, which is that there's no background occupation of photons at room temperature. So if I turn the lights out in this room, if I took an infrared camera, everything's glowing like this weird red color, right? But if I use my eyes, I don't see anything. So when you turn the lights off, basically, there's not enough thermal energy to create background visible photons. And so we can use that to basically say there's no background noise for our quantum channel at room temperature with visible and near-infrared light, and that's amazing for doing these applications. And of course, there's fun physics as well. So last year's, actually 2 years ago, anyways, last year's Nobel Prize in Physics was sort of related to these dreams of entangled photons and looking at non-locality and sort of distributed photon. So the types of electron spins I'll be telling you about are these defects in solids. So if I take a system like diamond, and I remove some carbon atoms, I get a vacancy, sort of a missing atom, and I can put that vacancy next to a nitrogen impurity. Now this NV center, this nitrogen vacancy center, this defect can trap some electrons, and those electrons have both spin structure and optical structure that we can use to form a qubit. And in particular, we like to think of these systems like trapped atoms in a solid. So we have absorption and emission of single photons, this interface to light, combined with a long-lived ground state that we can use to do quantum information processing tasks. And I'll describe this a little bit later. So this NV diamond is great. It's like a little trapped defect atom-like thing in a crystal. And these systems are amazing. They've been used for really sort of amazing proof of principle demonstrations and all these sorts of amazing applications for quantum science, like measuring molecules, doing quantum computing, teleporting quantum states over long distances. And I sort of always say this, but if there's one thing I hope you get from this talk, it's that this NV center in diamond, which has been a workhorse in the field for the past 15 years, is not unique. And on one hand, there's sort of different defects in diamond that one can utilize, but there's also defects in different materials that one can use to form a qubit. And so the material that I'll be focusing on today is this material silicon carbide, which I love. And over the past 5 years, we've discovered all these different qubits, all these different defects that we can form inside. And the one I'll be focusing on today is this die vacancy. So it's simply just a missing carbon atom next to a missing silicon atom in this silicon carbide lattice. So the next question you might ask is, okay, there's diamond, there's silicon carbide, maybe there's other materials. Why would you choose one material over another? And the first answer is that silicon carbide is a wafer-scale semiconductor. So here's a 4-inch wafer of silicon carbide and a tiny 2x2 millimeter chip of diamond. These two samples cost around the same price, all while silicon carbide is basically just imitation diamond. So it's used in fake diamond jewelry, it's hard, it's chemically inert. So if you go to the jewelry store and you buy fake diamond jewelry, it's either cubic zirconium or it's something called moissanite, which is just silicon carbide. So it's like fake diamond, but cheap and wafer scale. That's great. But on top of that, you can also make real electronic devices with it. So it's found wide use in power electronics. You can really dope it. It's a real semiconductor. And you can make things like LED light bulbs, 5G technologies, MOSFETs. And the real reason it's so mature today is because Tesla really likes this for EVs, for high voltage applications. And I always like to show this image, but the New York Times sort of wrote this amazing article which says, what are the materials beyond silicon that can revolutionize sort of our society and the technologies we have today? And they identified silicon carbide as one of them. And the reason I think this article's fun is because it features a photo of my hands holding a little chip of silicon carbide that'll produce some of the data that you'll see in the next few slides. And of course, for those engineers in the audience, there's also this huge Chips and Science Act in the US about boosting semiconductor manufacturing. And there's been billion-dollar fabrication facilities in silicon carbide popping up. And so there's this fun quote from the New York State governor that basically says, yeah, Silicon Valley, that's totally overrated. We're going to be making this new Silicon Carbide Valley. This is the future. So there's a lot of excitement about this material, which is very exciting for me. But of course, I'm not really a classical electronics person. I don't do power electronics. So the things that I think are relevant for hopefully some of you in the audience is the other features that we love about this material is our ability to make high quality factor on-chip integrated photonics with this material, and that these electron spins I told you about are very, very good quantum states that we can control. And so what we like to say is that silicon carbide is in this perfect sort of Goldilocks zone between our traditional quantum workhorse of diamond, and of course our old friend silicon, the classical workhorse for all the technologies around us, where we uniquely combine this ability to do sort of CMOS compatible wafer-scale electronics and photonics, and this optical readout polarization of these coherent single qubits that we can play with. And so to sort of outline what I'll talk about in the rest of this sort of presentation, I'll first just describe how we really use these systems, how they work, and how we can once again mediate interactions between them at long distances, mediated by light. I'll then tell you how we can harness this sort of doping capability to engineer perfect tunable single photon emission, which is what we want for these systems. How we can build photonic integrated circuits to enhance our ability to sort of guide and manipulate the flow of light for these sort of quantum systems. And then finally, if there's time, I'll describe the sort of final piece, which is hooking real computers up to that network backbone to do something useful, hopefully, in the future. So these defects in silicon carbide, right, they absorb and emit single photons. I can take a laser and scan over the surface of my sample, and I see these isolated, bright, luminescent dots that are each single photon emitters that correspond to our little analog of a trapped atom in a solid.
Professor,
Go for it.
perhaps a silly question because I don't understand chemistry at all. But when you say dye vacancy, I'm thinking of like a two particle or two body system almost.
Mm-hmm.
So I was wondering, whenever you see two systems, you'll see a 2-0 state, a 0-0 state, and like a plus and a minus state.
Mm-hmm.
Whereas over here you want, very consistent single band gap thing. So I'm wondering, is there ever concern of the dye vacancy that you have like two transitions or a degeneracy almost of the plus and minus?
So yeah, I mean, the answer is you don't really ever think about the band gap or the band edges. So I don't have a good image of this, but basically the way you think about this is you have your band gap in your crystal, right? So in that band gap, there's no states. These vacancies, what they do is they introduce mid-gap states that are far away from the bands.
Okay.
And then optical transitions go between internal orbitals in this defect that are still contained within the band gap. So the transitions between the orbitals of these electrons that are bound to this defect, they never feel the bands. There's no sort of problems there. What you were saying before was that there's two vacancies, the sort of, what the orbitals look like, how many electrons fill them, what the sort of spin multiplicity in orbital, those are important questions. And they have to do a lot with the details of this sort of structure here. You sort of need to think like a chemist, as you were saying. So I think some of those questions will be answered in this slide, but does that help a little bit?
Some.
Okay, yes. We can talk later too.
Thanks.
So partly to answer your question is in this dye vacancy, the ground state is a spin triplet. So there's not one unpaired electron, there's actually two, just because of the structure of the system. They sort of pair up to make this triplet state. So we have an ms equals 0, sort of a projection 0 magnetic state. And then we have this plus minus 1 state. That's totally fine. We just use two of them as our two-level system. Because it's a simple electron spin, we can apply DC fields to shift the energies around, and we can apply AC fields to do spin rotations. And this is the same physics that goes into like an MRI machine or an ESR machine. So we can use magnetic resonance techniques to manipulate this single electron.
Can you use strain in the crystal?
Yes, so we've actually done that. So this paper right here, we made a MEMS device, and we use sound to manipulate our electron spin, not microwaves. And that's one of the advantages of silicon carbide is you can make really sweet MEMS devices with it. So I keep saying the system looks like a trapped atom. We have a spin ground state, but we also have these orbital excited states. If we cool the system down to low temperatures, these orbital states resolve. Once again, like a trapped atom. You have your hydrogen, there's selection rules, there's optical transitions, there's hyperfine states. Same physics here, where we have our three ground states, and then we have these excited state orbitals that we can address with narrow line lasers. And once again, sort of analogy to atomic physics, there's selection rules. And it turns out that for this system, certain ground states couple to certain orbital excited states, and other spin ground states couple to a totally different set of orbital excited states. And those are sort of separated in frequency, and they're resolved. So if we take a narrow line laser, we can do spin-dependent fluorescence, and we can sort of play all the tricks from atomic physics to optically pump and optically read out our single spin. And if we combine that with this sort of magnetic spin rotation, we can do optically detected sort of rotations of a single electron in this solid. And I won't show you the details, but we can do this with extremely high contrast and gate fidelity. So we have very exquisite control of this quantum system. And one of the other benefits of being in this solid state platform is we're surrounded by a bunch of other atoms. That's a blessing and a curse. Some of those atoms have a nuclear magnetic moment. They're like little magnetic bar magnets. But the problem is they fluctuate all over the place. They cause noise, but those little bar magnets can also be other two-level systems that we can couple to and use as quantum memories. And we like this because nuclear spins are either the most or basically the longest lived quantum object that's known to science. Their lifetimes can be hours, minutes, days. And so having them sort of immediately accessible, and we can think about magnetically coupling to those nuclear spins, what we've actually been able to do is entangle a single electron and a single nuclear spin that are sort of locally in this lattice, and sort of think about using that as a quantum memory. Is there a question? And sort of this is the highlight reel. Other things that we've been able to do in this dye vacancy system in silicon carbide is we recently demonstrated what we think is the world record longest electron spin coherence ever measured in a solid. So basically we have the best electron qubit in a solid that's ever been measured with a coherence time that's over 5 seconds. And that's sort of an exceptionally long coherence time for these solid state systems.
What's the temperature?
This is all 5K. Is there the same question? Oh, nice, okay. I guess I should put the 5K over here or something. Okay, great. So how do we mediate interactions, right? I told you we have this spin-selective optical absorption and emission. If I do something like create a superposition state of sort of pointing up and pointing down at the same time of this electron, and I try to spin selectively scatter light off of it, I go from up plus down and trying to scatter light off to being up and scattering light plus down and nothing happening. And so this spin selectivity automatically sort of lets me convert a spin superposition state into a what we call spin photon entangled state, just from this sort of selection rules of this optical absorption and emission. And we can use that state to actually think about mediating interactions between distant qubits by having light do the talking in this sort of spin selective way. And we can do that just by interfering light on a beam splitter and using some single photon detectors. So how does this work? What we essentially do is an analog of Hunger-Mundell, or sometimes called DLCZ type interference. So we have a 50-50 beam splitter. We have two identical single photons that come into port A and B. And I mean truly identical, so same frequency, same phase, same arrival times, overlapping spatial modes on this beam splitter. It's really a stringent requirement. And if those two photons are truly identical, there's an interference that happens at this beam splitter where they like to either bunch up in port C together, or they like to bunch up in port D together. And this is sort of Hunger-Mundell interference. And quantum mechanically what this means is that you've sort of like erased the path information of where the photon came from, right? These photons are identical, they're exiting the same port. And so I can't label which of these two photons came from A and which of them came from B. And so that sort of erasure of path information of this interference effect we can harness. So if we create one of these spin photon entangled states at each of these ports, we do sort of interfere those states on the beam splitter, and we measure one single click and one single click only. In a sense, we know one of the two spins was up and scattered a photon, but we've erased the information of which one it is, and we know the other one had to be down because we didn't see two photons. And quantum mechanically, what that means is that we've actually created this entangled state, where if we measure one to be up, the other is down, and if we measure one to be down, the other is up. And so we can actually mediate long distance entanglement between two spins just by using light. And this can be at sort of arbitrarily long distances, which is what we like. So now we can dream about this quantum internet, entangling things over long distances using light. But there's a big problem, which is that photons aren't perfect. They're really, really good carriers of information, but they're not perfect carriers of information. So even at telecom, in the telecom band, you have something like 0.2 dB per kilometer. So what that means in practice is if I'm trying to send a single photon from, let's say, Stanford to Illinois, I have to try 10 to the 77 times to succeed once. It's totally unacceptable for anything quantum and for anything classical as well. And the reason that we can do anything is We just have amplifiers everywhere. Like all around you, there's just amplifiers everywhere. The problem is, quantum mechanically, we can't copy, amplify, measure, and repeat quantum states without disturbing them. There's this so-called no cloning theorem in quantum. Basically, the act of measuring something, looking at it, trying to copy it, disturbs it, right? So that's horrible, right? That means that my dream is dead. That would be really bad. So luckily, there's a pathway to get around this, and it's by building something called a quantum repeater. Now, this repeater works basically by breaking up your overall photonic link into segments. So if I'm trying to make A and C entangled together, what I'll do is I'll introduce an intermediate node B. And first, I'll entangle A and B together using this sort of photon-mediated scheme. Then I'll take half of the entangled state that was at B and store it off to the side in some quantum memory. Just say like, hey, hold on for a second. And then I'll entangle B and C together. And once at B, I have 2 halves of 2 separate entangled states. I can do a local measurement and gate to sort of fuse those overall, sort of 2 independent links into one overall link between the end nodes. Sometimes this is called entanglement swapping. It's sort of a form of quantum teleportation. There's lots of funny words describing how this works. So the other question is, like, why would you do this trick to make these 2 end nodes entangled? Well, basically what you've done is you've turned one very improbable success that requires you to transmit a photon over the whole link length into 2 sort of independent processes that are totally separated that are much more likely. So basically what you can do is you can have some high probability thing, have it work, hold on to it, and then do something else that's high probability that'll work, and then combine the 2 instead of waiting for this sort of exponential link to work. And mathematically, it looks like something like going from exponential scaling in distance to something that's polynomial in distance, which means that this 10 to the 77 number turns into something that's way more reasonable. Now, the nice thing is that we can realize this tech with these spins and solids. We can entangle them over long distances. We have these nuclear spins I told you about as local memories. And so there's some things we need to do to make this go. But what I'll focus on for the rest of the talk is this requirement I told you about, having those photons be indistinguishable, having like really coherent single photon emission is really hard. And actually, if they're not perfect, this entanglement doesn't actually happen with high efficiency. And that's where the sort of next part of the talk comes in. So we can actually take these electronic devices that I told you about, like the same wafer that might go into a Tesla, they might be shipped off to Elon somewhere, I don't know where he would be getting these chips, and we can just get a PIN diode, a very simple electrical device. And inside of this intrinsic region, we can introduce these defects. We can measure their luminescence, they're good single photon emitters. So here's a bunch of these randomly distributed defects in this sort of commercially made PIN diode. Why would we do this? Well, I told you that getting these photons to be indistinguishable is hard. One of the reasons that they're hard is because each of these defects in this solid is its own special butterfly. There's a little local strain, local stray fields that shifts the emission frequency around so that each defect is emitting at a different frequency. And that means that this interference with the beam splitter wouldn't work. If you're an atomic physicist, every atom is the same, there's no problem. In a solid state, each defect is a little special. But we have this ability to apply electric fields and do Stark shifting, or use the Stark effect, just like in an atom, to shift our emission lines so that they overlap with each other. And because we have this thing in a PIN diode, we can do high fields in a very controlled way, sort of integrated in this device. So we can take this narrow spin selective optical structure and we can tune it by over a terahertz just by applying a voltage. So this is sort of an extreme amount of tunability. It accounts for something like 40,000 line widths, or many, many orders of magnitude over the sort of variation between different defects. These are 3 tuning curves with bias for 3 different defects. And they have different slopes and different shapes, and there's interesting things to understand about that. But what I want to draw your attention to is that some defects, you apply voltage, and then the emission frequency doesn't change, and it doesn't change, and it doesn't change. And only after reaching about 100 volts does it start to shift. And this is sort of maybe a small detail, but it's important. And for the electrical engineers in the audience, maybe this is sort of familiar to you, but the problem here is we have a p-type layer, we have something that we think is intrinsic, and then we have an n-type substrate. The problem is our intrinsic layer is slightly n-type doped. And we know that we put a p-type semiconductor and an n-type semiconductor together, We get this depletion region at the interface, so our electric field sort of gets dropped with this sort of triangular shape at this interface. And the problem is this is so n-type doped, or sort of unwanted n-type doping, that this field region only penetrates partially through our intrinsic region, and only by applying larger and larger reverse bias does this triangle sort of grow and go deeper and deeper into the crystal until it finally drops uniformly.
Can you compensate that charge?
Yes. So in higher quality materials, they introduce vacancies to sort of suck up those charges. So it just turns out that for this material is a little bit.
Doping, right?
Sure, yeah. This is N, but yeah, you sort of effectively slightly
Your-
p-type it, yeah. So, this red line took a little bit of voltage. It's simply just saying, hey, it was a little bit deeper, and it took a little bit more voltage for that field profile to reach it. So it'll become obvious why I'm talking about this in the next slide, because it's not very interesting in its own right, but it becomes important for understanding what comes next. So there's this field profile and this sort of depletion physics in the semiconductor that's driving how these fields are moving around in this device. So we have this optical emission, we're applying voltage, at first nothing happens, but around 70 volts it starts to shift, but it's not just shifting, it's also narrowing. And that's really exciting because I told you that each of these defects feels local strain and local electric fields, and I can shift them with electric fields. And actually, solids are just horrible places for single photon emitters to live because they're sensitive to stray fields, and solids are just noise. There's free electrons and holes everywhere. They're fluctuating around. And so our line basically jitters around because of this local electrical noise. We call this inhomogeneous broadening. It actually turns out that our system is so sensitive that we can sense the presence or the absence of a single electron, something like 200 nanometers away from our defect. So if there's any fluctuating carriers, you're screwed and your line gets broad. But that's why this narrowing is very exciting. Because this narrowing is basically telling you that under zero field, you have this fluctuating bath of crap, right? And if you start applying a field, you get this electric field in your crystal, you get this depletion physics. Those electrons and holes, they drift and diffuse away from your region of interest until you're left behind with a near perfect environment for your quantum system to live in that has no fluctuating carriers. And there's nothing weird going on here, it's just the same physics as a PIN diode or a PN diode, where there's no fluctuating carriers in this depletion region. So our system is basically almost Fourier limited, so it's almost at this fundamental limit of how good this line width can be. It's rock steady over 3 hours. We can tune it 40,000 line widths. So it really turns into this sort of almost ideal single photon emitter.
This is in reverse bias.
Yes,
But you're above the breakdown.
below the breakdown.
Yeah, the voltage is less than.
Yep. And that's one of the benefits of having this be a high
Having this
breakdown.
Yeah.
Yeah. So we can sort of, actually, we were not limited by the breakdown of the semiconductor. We were just limited because we had a Keithley source that went to 200 volts. That was it. We could have gone more. Maybe we should have. But and so this thing narrows, which is great. And so if I told you that these photons need to be indistinguishable when they hit the beam splitter, if both of them are jittering around in frequency, that interference doesn't happen with high fidelity. And it turns out that basically a factor of 50 in narrowing, which is what we showed for two photons interfering, is maybe something like a factor of 50 squared in the speed up of the interference.
What temperature is that using?
This is all 5K.
I have another question.
Sure.
Does it matter how deep your defect is?
Yes, so it basically just sets the voltage at which this depletion happens. The problem as well is, like, if this defect becomes too close to either of these dope surfaces, each of those dope layers is like a big fluctuating bath of stuff. So that's also a problem. So it does matter a little bit, but those are sort of the trade-offs. Okay, so next part, which is I guess why I'm here at all, is making photonics with this platform and using it to do better sort of quantum interactions, right? We want light to do the talking, and so making photonics to guide and enhance that interaction is sort of the next step here. And so, if my dream is to make these silicon carbide networks, really we've gone through and we've hit a lot of our check marks that we want to do to make a great system. The really only remaining thing I would say is that dipole sources of light, things like light bulbs, LEDs, not lasers I guess, but dipole sources of light, they shoot photons everywhere, right? They're quasi-isotropic broad emitters of light. And if I want photons to interact with something and mediate interaction, I don't want a photon to go hit a wall and do nothing for me that's useful. And so actually, this is a problem, but of course there's a nice solution from optics, which many of you probably know, which is if you put your two-level system in an optical cavity, you can engineer the density of states and basically funnel its emission into a particular spectral mode and a particular spatial mode. And that's exactly what you want to do. You basically want to shoot those photons and have them interact with another quantum system, not go over and do something that's not useful. And so we can do this through this Purcell effect, basically having very high quality factor photonic devices that are also small mode volume. And so if we have high Q, small mode volume, we can do this sort of energy funneling with very high efficiency to make ideal single photon emission that's not only narrow and tunable, but also directional. So we want to make silicon carbide photonics, right? So many of you are probably aware of the wonders of silicon on insulator or silicon photonics. So basically we want to make silicon carbide on insulator and silicon carbide thin film photonics. So step one is you make a thin film on insulator or on a lower index of refraction material. Once you have that thin film, you can etch it into waveguides that are surrounded on all other sides by a lower index of refraction material, so that basically the light gets trapped in this waveguide and you can make structures that guide light on your chip. The way that we make these thin films is very stupid. There's a few ways you can do it, but the way that we like is very stupid. We take this quantum grade silicon carbide, we bond it to either a silicon thermal oxide wafer or just glass. We stick them together, and then we take a grinding wheel, or basically sandpaper, and we mechanically remove 99.999% of the original material until we only have a micron film left. We go over with a CMP, we make it smooth and perfect. And then, once we have that film, we can etch it using very easy etching techniques into nice high quality factor optical resonators all on a chip. So here are some ring resonators where sort of the light is circulating in this ring. The etches look great, which is a big plus for us, especially over diamond. The losses are very low and the quality factors can be quite high. So we have this ability to make high Q, low mode volume, integrated photonics, all in silicon carbide. And over the past few years, we've really been sort of boosting up the quality factors in the system to sort of almost 10 million, which we're sort of excited about. Not only that, we're also pushing towards the wafer scale. So here's a photo of me holding a 4-inch wafer of silicon carbide bonded to a thermal oxide wafer. So we can start dreaming sort of big integrated photonic streams. And sort of the result of those advances is basically, we think we have all these check marks that we need to do something useful. We have great spins, but we also have great scalable photonics. What I didn't show you is we can also put these single spin qubits inside of those photonics and they remain fairly coherent. So we think we have all these check marks to maybe realizing some of these big dreams for quantum networks. So I hope I've sort of gotten you a little excited about this silicon carbide platform. We have sort of the best spin qubits that have ever been measured. They work at 4K. We have this narrow and tunable single photon emission. We have these nuclear spins that we can play with that are super long-lived. And we have these scalable high Q photonics for doing like wafer-scale quantum science using the same wafers that Tesla gets, for making these repeaters, and maybe even dreaming dreams about doing photonic integrated circuits and photonic quantum computing, all monolithically in silicon carbide. And so, I think this can make a awesome quantum network backbone, but of course, these defects don't actually make useful quantum computers. And that's sort of a problem, right? Like, I have a network, but it's not hooked up to anything useful. So like, Chris, why did you spend all that time talking about this? So that's what we're gonna tackle in the last 10, 15 minutes of this presentation. And so that's where this idea of a quantum modem comes in. How do we hook up computers to this fiber optic, light-based entanglement distribution network? So our dream looks something like this, right? We have our quantum network backbone, and then we might have something like Google's superconducting quantum computer. Now, Google's superconducting quantum computer, it operates in a dilution refrigerator at 10 millikelvin or something like that, and at around 7 gigahertz. So it's gigahertz frequencies, super low temperatures. But our optical network and sort of long range, long haul communications, right, they operate at 300 Kelvin and 200 terahertz. So we have a factor to make up of around 30,000 in both temperature and energy, and converting these microwave states into optical states to send them along in this quantum network, to then eventually entangle two Google quantum processors together. So luckily there's a way that we can do this that's pretty simple. Just uses nonlinear optics or electro-optics. So right, electro-optics tells you that I can change the index of refraction of a material by applying an electric field related with this Pockels coefficient, which basically just tells you the nonlinearity. And if I can change the index of that material, I can change the phase of light as it passes through that material. And for those of you that speak nonlinear optics, this is related to the so-called Chi-2 nonlinearity, which is a quote-unquote three-wave mixing process. And what that means in practice is that I can have an optical tone coming into one of these nonlinear crystals. I can come in with one of these microwave signals, and those two frequencies mix together, giving me a modulated optical signal that sort of encodes my microwave information as a modulation in an optical signal. And you can use this to sort of encode your microwave state at an optical signal and send it along a network. But the problem is the efficiency of converting a single microwave photon into this sort of modulated optical photon is related to this Pockels coefficient squared. And so if this nonlinearity is weak, these efficiencies are really, really bad. And so the reason that we don't have an internet of quantum computers today, at least in part, is because materials are just not nonlinear enough to mediate this interaction with high efficiency. So that's the key problem, is most materials are just not nonlinear enough to make this go. And so we got really excited about this problem, and we started evaluating what are the common nonlinear optical materials that are used today, and how can we understand them and maybe do better in the future. So there's this great plot from IBM which shows all of these different nonlinear optical crystals and their Pockels coefficient. And this is a log scale, so these are like massively different systems. And there's obviously a huge range here, so how can we understand why is BTO and KTN so good and why is glass so bad? And if we can understand that physics, maybe we can pick something better moving forward. And luckily, there's an easy way to understand this physics using a heuristic from optics called Miller's rules. And Miller's rules simply just state, if I want three waves to mix together in my crystal, I better be linearly susceptible to the three waves that make up the interaction. Right? So if I want to mix three things together, my three things have to make it into the thing that mixes them. And this linear susceptibility, this Chi-1, that's like the index of refraction, or the dielectric constant. That's your sort of standard susceptibility. And so this three-wave mixing term is proportional to the Chi-1, or the linear susceptibility, of the three waves that make up the interaction. And these higher order nonlinearities are susceptible to then the four frequencies that make up the interaction. But this is great, because this lets us design better materials moving forward. For electro-optics, some of these susceptibilities are high frequencies, some of them are low frequencies, right? It's microwaves and optics, 30,000 difference in energy between those. And that's great because materials have drastically different susceptibilities and different frequency ranges. So basically every optical material that you know has an index that's somewhere between like 1 and 5 maybe. But the dielectric constant, sort of DC susceptibility of materials, can be like 0 or like 100,000. Like there's this huge variation because there's this extra contribution from slower responding dipoles in the crystal that you can actually engineer that don't have any sort of like infrared or UV vis response, but can really make the susceptibility in the microwave regime very, very, very high. And so in practice, if I can't engineer the index, maybe what I can do is look for materials that have really strong DC dielectric constants. And if I want Chi-2, I want this thing big because I get a linear term with it. If I want Chi-3, I want this thing big because I actually get it squared. So the moral of the story here is if I want nonlinear optical materials, what this tells us is I just want materials that have high DC dielectric constants. And that's great, and it completely explains this entire trend, which is awesome. The problem with this trend is these materials were all measured at room temperature. And so if you want to do quantum nonlinear optics, you need to find materials with a high dielectric constant at low temperatures. So we've understood the physics, we only want to find high dielectric constants at low temperatures. So the types of systems that we can use to find these high dielectric constants are these ferroelectric perovskite materials. So there's this B4 ion that rattles around in this oxygen octahedral cage. And basically it can sort of like displace upwards or displace downwards, giving a net electrical polarization that basically points up or points down. And in analogy to ferromagnets and paramagnets, you can have ferroelectrics and paraelectrics, where there's Curie temperature, or TC, where above that temperature, the system's nonpolar. It sort of looks harmonic, so this is electrical polarization and energy. If I try to perturb it, I get this sort of harmonic response of the crystal. But as I approach this phase transition temperature and I cross over between an unpolarized state and dropping into one of these two wells, the energy landscape looks super flat, which means I can have drastic changes in the electrical polarization for basically no energy cost. And then of course, I cool down further and I drop into one of these harmonic wells again. What that means in practice is that the dielectric constant, or sort of the epsilon of materials, as I approach TC, blow up. And so if I want to engineer a high dielectric constant, I want to find a system that approaches a phase transition. And in this case, I want that to be near zero temperature for quantum physics. And so I want T to be close to zero. So we've understood the physics that's guided us to this fundamental thing, which is we just want to find low temperature phase change materials. Once we can do that, we can do awesome nonlinear optics at low temperature. The fun part is we found this material. It's strontium titanate, so for condensed matter people, this is an old friend. For people who like fake diamonds, it's also a fake diamond. It's one of these ferroelectric perovskites. And what's great about strontium titanate is, first of all, it's been studied for like 50 years. And if you cool the system down to low temperature, its dielectric constant explodes and goes to over 20,000 in basically all quantum relevant temperatures. And importantly here, it goes high and then stays high. So I told you here, you approach this phase transition, your dielectric constant explodes, but then of course you drop into one of these wells and then it goes down again. In this case, it goes up, and basically no matter how cold you go, it never crystallizes. It never undergoes this phase transition. So this is sort of cool. This is related to something called this quantum paraelectric phase in strontium titanate. Basically, instead of dropping into one of these two potential energy wells, this barrier is so small and this mode is so floppy that 0-point fluctuations always sort of bounce you back and forth between these two wells, and you never actually crystallize a phase. So you're always continually approaching a phase transition, but you never reach it. And that's actually great, because that means dielectric constant's always high, and it's consistent over our entire temperature range. In this case, that also means that our system actually never undergoes this phase transition, it never becomes polar. So our response to DC bias is only ever quadratic. But since we get sort of this quadratic response with electric field squared, but also dielectric constant squared, if dielectric constant's big, we don't really care. But it does mean that we have to bias this crystal to make it nonlinear. And so we can actually do this and measure. So we can take a piece of strontium titanate, put it in a cryostat, bias it, and measure its index of refraction change by putting it in a Mach-Zehnder interferometer, where we encode the phase change induced by the material as basically an amplitude change in the output of this interferometer. This is once again, a quadratic electro-optic effect, so we have to bias it, but once again, epsilon's huge and we have to square it, so this effect can become quite large. We can go and we can measure this response, and indeed, with 0 applied bias, nothing happens. We apply more and more bias, and the nonlinearity grows and grows and grows. And already with a bulk crystal, 1 millimeters, applying just with like a regular DC power supply, we're seeing nonlinearities that are at least 10 times greater than what lithium niobate has. It shows this temperature dependence, right, where below 1020 K, it's high. So it has this sort of quantum paraelectric temperature dependence. But of course, having a 1 millimeter crystal with a DC power supply across it is not the end goal here. The end goal here is to have some like lithium niobate-like integrated photonic chip, where you have electrodes that are biasing the system, but not over 1 millimeter, but over something like 5 or 10 microns. And so, we actually don't know when we bias more and more what the ultimate limit of this nonlinearity will be. So we've already measured something that's the most cryogenically tunable optical material that's ever been measured. It beats lithium niobate, barium titanate. We don't know how high it will be. We really think that we can start pushing towards this transduction dream of microwave-to-optics at low temperatures with efficiencies that approach something like 1. So, we have lots of dreams, right? Part of our dream is to use this silicon carbide to mediate long-distance entanglement. Our other dream is to sort of build these quantum modems by exploring wacky condensed matter systems and harnessing their nonlinearities for photonics, to build this dream of the quantum internet. As I mentioned, this work is sort of a mix of what's been done both at Chicago and Stanford. And I showed this at the IQUIS talk, so I'll show it again. But as is mentioned, I'm here now full time. We're building the labs. We're over in ESB, the North Building the building north of MRL. So the labs are a construction war zone, but they're being built. And technically my affiliation is material science. And I guess at some level it's because they put these posters up in the material science building. And I really do believe, if you really want to revolutionize quantum tech, you need to develop these new materials, silicon carbide, strontium titanates, that give you new functionalities. And if you want to sort of beat the limits of the current semiconductor industry, you need to develop new semiconductors as well. My other shout out is we had the cover article of Physics Today, I guess 2 months ago now, that outlines sort of the dreams of silicon carbide, so you should go check that out. As was mentioned, I'm sort of primarily in MATC, but I have affiliations in physics and ECE. I have I need help really bad. So I'm recruiting at all levels, postdocs, undergrads, grad students. So if you're curious about that, I'm happy to talk. I'm over at MRL 212. Feel free to knock on my door. Yeah, and thanks for your attention. I think that sort of ended right on time. So happy to take any questions and to chat with any of you afterwards. Cool.
We have plenty of time for questions.
Do you need process enhancement to see the interference?
No, it just becomes really, really low probability of success. So the sort of best experiments that have ever been done in the field, they don't use photonics, although actually there was a paper 2 days ago. Anyways, they don't use photonics. They just collect light from the crystal with a high NA objective. That collection efficiency is something like 1% if you're doing really, really well. And their entanglement rates between distant spins is something like hertz or millihertz. So the links work. You know when they work because it's a heralded interaction. It's just not useful because it's so slow. Now, if you were able to get 100% and have things be directional and also that's where the photonics helps you. So it works as is. It's just not very useful.
I'm somehow troubled at a fundamental level that you found a material that you can cool it down and it never drops into its lowest energy state. And that there is this, even at the lowest temperatures you're looking at, there is this quantum uncertainty about its arrangement of atoms.
Mm-hmm.
It's
pretty wild, yeah.
And so when I think about that, that suddenly makes me think that there's something else, when you have that uncertainty, there's something else either that you know really well or you don't know really well. Huh?
Mm-hmm.
And so I'm wondering, you're looking to use this to transduce between microwaves to optical,
Mm-hmm.
but yet there's this fundamental noise
Mm-hmm.
in that system. So somebody, that's what's kind of troubling me. I'm trying
Yeah.
to figure out the.
No, I mean, I haven't really thought about it that way before. Because I guess in a regular nonlinear optical material, you cool it down, it's in that lowest well, and it's there, it's got a well-defined position of all the atoms. And here it's in this sort of weird state where it's even unsure where the atoms are. I will say, in that state, it's not a nonlinear optical system. So what we do is we actually bias it. And I think one way of thinking about it is we actually determine which way all the atoms should go. So by applying a field, we sort of crystallize a phase and sort of pick a direction. And then all those atoms are in place, pointing along the direction we're applying the field. So if that is a problem, I think it probably wouldn't be a problem for our particular use case because we are applying this large field that basically, one way of thinking about it is it tilts this whole potential landscape and then you sort of fall down into one side. And so your question, there might be something there, but I think in our case it doesn't really matter so much.
Well, actually, what the answer is that it's not just going down to zero, it's going down to zero in the presence of this field.
Yep. Cool.
So, I think it's on slide 13 or something, but where you're going to show the graph where, essentially the threshold voltage shifts depending on where your,
Defect is,
defect
yeah.
is. So you explained why there's that shift in threshold voltage. Do you know why there's the difference in essentially slope of that?
That's a really good question. So there's some details I swept under the rug. So silicon carbide is a hexagonal crystal, and this die vacancy is 2 missing atoms. So those 2 missing atoms can like orient a bunch of different ways in that hexagonal crystal. And each of those orientations has a slightly different local crystal structure and has a different susceptibility to field. And so basically it turns out that these 3 defects happen to be 3 different types of orientations, which is why they have different slopes. Good eye though. Yes.
If you could go to the slide where you had the directional control.
This one?
I think it might one, a little bit before you mentioned having controlling the direction of the output of the photon.
Yes. This one, I think.
Yep,
Sort of
and so
shooting
there's
it
a
out.
mirror over there, and I understand that there is statistical peak, which the more photons you have, the narrower you get, and you know how many reflections on average you require to get out. The question I had is, effectively when you're controlling for direction over here with mirrors, you're creating a small path length difference. And I was wondering what's your sensitivity to path length differences in terms of interference, because you know that is something which I was considering.
So I'm not sure if I understand your question fully, but the sort of defect is in one particular location and it doesn't move. And then the cavity mirror, the mirror positions also don't change.
Mm-hmm.
And so those 2 things set all the phases in the system, and there's no sort of interference problems, I think.
That's not okay. Let me clarify this. I'm saying there is a reflection process, right?
Yes.
And it's a partially transparent mirror,
Yes.
which means for every cycle, there is probability P such that it is transmitted.
Yes.
Which means for different photons, you'll have a distribution of how many cycles it is before transmission.
Yes.
And each cycle introduces a delta L.
Mm-hmm.
So my question is, if you have a distribution of how many cycles you take,
Yeah.
how sensitive is it for this thing took 1 cycle, this thing took 1,000,000 cycles, and that
Okay.
is.
I understand your question now. So there's 2 things here. One is we have this 2-level system. We bring it up to the excited state, it radiates light. Problem is it doesn't do that immediately. It has some lifetime that it lives up in that excited state. So sometimes it radiates immediately, sometimes it takes 10 nanoseconds to radiate, and there's a phase difference there. And so your wave packet has some very particular shape of sort of, the spreads of all those phases giving you, some 10 nanosecond wave packet. So that fundamentally we can't change, we can't get around. And then there's the second question, which is you put it in a cavity, and then there's this extra sort of shaping of that light that you do, depending on sort of the cavity line shape, which is sort of the inverse relation of the question that you're saying. So those things do matter. They change the shape of the output wave packet, the spread of phases and frequencies. Fundamentally, as long as this wave packet coming from one emitter and the wave packet from another emitter look the same, how broad or narrow it is doesn't really matter. But what that means is that you want one emitter that's in one cavity to look exactly the same as another emitter in another cavity. And so if the mirror reflectivities are slightly different, or if the atom has a different lifetime, you can sort of have some problems. Another way of putting this is like the Purcell effect reduces your radiative lifetime, right? So I think these things are basically related. So putting things in a cavity makes the emission shorter. It also gets sort of filtered through the cavity. So all these things play off each other. But they don't really matter at the end of the day, as long as the photons are identical. In practice, what it does is, I don't have a good figure, but when the photons interfere with the beam splitter, their length determines sort of the coincidence window of this interference dip.
Mm-hmm.
And so if they become too narrow, or sort of too broad spectrally, too narrow temporally, the detector isn't fast enough to like see these time delays. And so there's a technical limit you reach that's around 50 picoseconds. So as long as you're in this sort of nanosecond lifetime, you basically never hit that limit, and it doesn't really matter so much.
Thanks.
Yeah, I don't know if you covered this or not, but I was kind of curious about how you excited your qubit. I'm most familiar with like the T-center, and you need like 2-color excitation to really make that happen. So do you do the same thing, or how do you?
So we do like super simple. So we have our crystal, we just have a microscope objective. We come down from the top down, and then it luminesces back towards our objective. So there's no like, you know, excitation and collection are like, you know, at 90 degrees from each other. There's no pump probe thing. It's just like, in practice, what we do, I shouldn't even figure about this, but we pump at one frequency, and then the emitter emits very broadly, and then we spectrally filter our pump from our emission. So there's a spectral filtering that lets you do this, because otherwise your laser just blinds your detector. So we have a spectral trick that we play. Because as you said, you can do like a cross-polarized thing to reject your pump. In this case, we do a spectral filtering to reject our pump. You can also do time filtering, like you can give a little 1 nanosecond boost to your system. It goes to the excited state, and then, you know, by the time it luminesces, your laser's turned off. You can also do tricks like that. Time, polarization, space, frequency. Those are your toolboxes for doing filtering.